beams. Then it hits the sample. And as I told you, many events occur. Photoelectric effect occurs, deflection occurs, backscattering occurs, transmission occurs, all sort of events occur. And those events, the electrons undergone all the events which are transmitted come to the objective lens. And objective lens again organizes the electrons. The ones which are scattered at larger angles are excluded from the information. And the ones at the required angles, at the low angles, are come to the objective lens. Then the objective lens keep the beam intact, so that when the electrons comes here, and if they go this way or this way, then they will be of no use. So the protocol stop role is done by the objective aperture, that after undergoing that events, after the interaction with the specimen, the beam is again coated by the objective lens, and each lens then magnifies it as well. So on one way they are removing the large angle scattered beams, and in the second place they are magnifying that beam as well, because they are not losing the magnification. So when they pass through the objective lens, again there is a chance of large angle scattering, and that large angle scattering is again dealt with by the objective aperture. There is an objective aperture after that. So whatever that could not be focused on to the relevant area by the objective aperture, they are by the objective lens, they are excluded by the objective aperture. Okay, so after refining that beam and magnifying that beam, after the objective lens, you need something to direct that beam onto the fluorescent screen, and the lenses which do that job are called projecting lenses. Here is the silicon, what they have written? Projective. So this is probably some German writing, they are writing K instead of C, right? So the projective lenses then project that image or diffraction onto the viewing screen. The viewing screen, it is a full screen at the bottom. You have visited the lab. I have shown you those who visited, right? And those who didn't visit, come to my office collectively, and I will give you a brief tour to see what is practically available there. But I took the previous students and I showed them in detail that how the electron microscopes are working and how they look like. You have like this screen, and in the middle you have a small screen. So if you are interested in very high magnification, then instead of this whole area, you pick up this screen and they take this bit of the image and you look into it with a further higher magnification. So if the magnification there on the screen was 1 million, then by using that, you bring that to the ocular focus, when you are looking into that screen, it appears 10 times more with the eyepieces. So 1 million time magnification was done by the microscope, and then you are looking into the image with another 10 times magnification. So it made 1 million into 10 millions. And when you are doing very fine focusing, then people advise to use that central screen, and people do it. Let's move forward a little bit. I told you the manual way, that when the image reaches here and you open that screen and you take the image, it comes upon the negative, film, and then in our times we used to develop the film in the proper solution, then we used to fix it with the fixing solution, then the film used to be put in water for 20 minutes or 30 minutes to wash them so that all the chemicals are washed away from it. Then we used to put it in the drying cupboard for overnight, and when it was dried, then we used to take it to the photographic room, and in the photographic room we used to put the film here, fixed in that photography. The light was switched on the top and the film was visible down here. And here we used to put the photographic plate, right? So from here to here, you have a choice of 100 times magnification. So the 10 million magnification you were seeing, the 1 million magnification, because you are not taking image with the eyepieces, right? So the 1 million magnification was there, and when you enlarge the negative, then you converted it into 100 million times. And here you have a great choice. By displacing the film level up and up, you can increase the magnification 100 times. And there are different levels. I will explain them in the later times, but a time will come that we will discuss these. So throughout the microscopy process, you have various ways. Instead of that traditional manual camera, nowadays people are using the digital cameras. Some people try to take image from the screen with ordinary camera. That image can be showed to an illiterate person that yes, I have done a microscopy, but technically that image has no scientific information, because you are talking in terms of nanometers and angstroms, and when you are taking image from here, you are taking from here or here, so there is no trust that how much magnification was done when you are imaging something, right? So that is not technical and never advised. What is advised is through the manual proper set camera or the digital camera connected with the microscope. And when I was looking for the CCD camera to be directly connected with the microscope on the top, and it transforms the image, translate the image onto the computer screen, its price was in those days about 40,000 pounds, right? So it is not a cheap business. When you are doing microscopy, a lot of funds are required to add these accessories. But CCD camera is very accurate, and you can use the computer images for interpretation purposes and for diffraction measurements. So this is a ray type diagram that you have a condenser lens, then the beams come onto the, so look into that. that the beam spreads and the condenser lens again condenses it. It again spreads and again it is condensed. And in this way you reach here. So the magnification and the condensing are done simultaneously throughout the microscopy process. Here is the sample, here is the interaction, then the objective lens, then the objective aperture, then the projector lens, and then the screen. And when you pick the screen, here is the camera. This is the simplest possible view of the electron microscope. Now, and actually it is not that, because the condenser lens has its own assembly and its own filtering out of the rays. So people are now using, when they are going towards the high resolution microscopy, then they need further and further refinements. High resolution electron microscopy means that you are interested to look into the atomic planes. After optical microscopy, the technique developed were conventional transmission electron microscope. After that, the machine developed was conventional scanning electron microscope. And conventional means that it has a micron level resolution and you can look into a polycrystalline material where the size of the crystals is from 1 micron up to a few microns. But when you are interested in looking into the atomic spacings and looking into the dislocations in the planes, when you are talking of crystal defects, you are talking of dislocations of the planes, then you need something which can show you directly the spaces between the atomic planes. And that sort of microscopy is called high resolution microscopy. So when you are moving into higher resolution, the diffraction pattern is done similar in both cases. But when you are interested in looking into atomic planes or in the diffraction, you are interested in further resolution, convergent beam electron diffraction or like that, then you need high resolution electron microscopy to resolve fine features. When you want to resolve fine feature, then you need to further control the electron beam. Because if electron beam is like this, these two rays are coming, then they are passing here and giving me an image here. But if instead of it 10 or 15 rays are coming and all are just crossing like this, and here I see something, it will be highly confused. It will be very bright, as I told you about the flashlights. You can't see things properly. So you increase, look at my hand, it looks like this, and if I decrease or increase the light, then the contrast will change. And when the contrast changes, it makes you things which are invisible at the high intensity beams. If you are looking into my hand, and if it is here in the bright area, then it is not more resolvable. But if I take you here, then some features appear. And when you are talking of very high resolution microscopy, then the perfect focus doesn't give you the visible, the most convenient resolution of fine features. And for that you are defocusing, that if the focal point is here, you slightly take it one side or the other side and you slightly defocus it so that the fringes appear at the edges, and that is called the phase contrast microscopy, where fine features are resolved. So here you see again the electron gun, then a node which pulls the electron guns onto the column of the microscope. Then you have the gun alignment coils. If you remember, in the electron gun, I showed you some pictures like this, that the gun aperture is here and the alignment is here. So if the gun is like this, right, it is like this, the shape is like this or like this, directly or like this or like this, then when in the start it is tilted, this can be aligned by gun alignment coils here, so that it is perfectly in front of the aperture, so that it passes the electrons perfectly onto the condenser lens. If it is a little bit tilted, then you may increase its currents twice or triply or 4 times or 5 times. Still, it will not give you the desired intensity beam, because you are dealing with the electrons and they must